Good afternoon. Good afternoon, everyone.
Good afternoon.
Good afternoon. How are you?
Good, I guess. Wait, so we're on lab 3 now, right? Oh, do you see my email? I'm not sure. The last section was like in there. It was just in text form. Do you see my email? I sent you email, but you never responded back. So I'm not sure if you received it.
I first saw your email, but when I tried to respond, but I didn't find your email, and I sent you an email back asking you to send my. I'm not sure if it's.
I didn't receive it because I was looking all the time for it, but like I didn't see your email response. Can you send me another response, I guess, back then?
Can you resend your email? Because I didn't find your email. I saw your email first time, but then I don't know why.
Okay. Just have to. Okay. How do I? I'm not sure how to resend. I'll just forward you it. I will just forward the email to you since yeah.
Okay. Sounds good.
Yeah, do you receive it?
Not yet.
Oh, there it is. It's right there. It's right there. Oh, you just exit out of it.
Okay.
There it is.
Okay.
Like you said, I was missing the fourth part of the experiment, but that was already in the doc.
But I didn't say it's in the doc.
Yeah.
I think you only included in the first 3 parts.
Yeah, that was the fourth part that was in there. I guess it's pretty easy to miss since it's like not really like, yeah, it was just in there. So like I guess, yeah. But this is kind of like responding back to the Blackboard message. So like I guess you kind of have to like read the original Blackboard message to like get the context of like what you. I was sort of like trying to like respond to that. Let me see if I can like. Content. Okay, so you said, do you miss the fourth part of the experiment? I did graph in Excel. In the text message in the chat right there. This is what you wrote to me, and I did plot the graph in Excel. I just copied the graph from Excel and put it on Google Doc. That's what happened.
After, how about we discuss after this?
Okay, yeah. Okay,
yeah.
clear.
Thank you. Let's share my screen. Good afternoon, everyone. So last week I asked you, not last week, 2 weeks ago, I asked you to do a poll, like how often do you want to meet for this lab? So this lab is supposed to be one today, and another is a lab recitation. If you have any questions, you can ask for the in the second session. So I got in total 25 responses. I need to see responses from you guys. Where's the chat? Okay. And so if you, I put a link here. This is for the still for the questionnaire. How often do you want to meet? I would like to collect everybody's opinion on how often we meet each week, or we meet weekly or bi-weekly. So yeah. So if you haven't responded to this link, then please fill up your preference, what you want to meet, how often do you want to meet. And today we're gonna do lab 3. wait, where's my Google? Okay. You guys can see my screen?
Yes.
Thanks. We do measurement of liturgy. So today's lab is kind of fun. So you basically, we will play with this equation. So we know the Newton's law of gravity has the equation F equal to G. This is the gravity, this is gravity, and times the mass between two objects, and divided by the distance between those two objects with square. And so we also know F equal to mg. Let's say if you're standing on the earth, so your weight will be F equal to, so the force you put on the earth is F equal to mg, which is your weight. And so the weight is coming from the interaction between you and the earth, the planet. So if you take, so remember that we call this equation as 1, F equal to G m1 m2 over r square. And then we have another equation, we call it equation 2, which is Fg equal to mg. So this Fg equal to this F. So if we put the equation 1 equal to equation 2, which is make these two equals to each other, then we can cancel out the m. So the m is your weight, is your mass. So then we get the, so we say we get this is when we put the equation 1 equal to equation 2. Then you by canceling out the m, then you have a g equal to g e over re square. So here the g is still the constant, the m is the mass of the planet because your mass is cancelled out, and the r is because which is supposed to be the distance between the center of your mass to the center of the planet, but because the distance, so because the planet is so big, and the distance could roughly equals to the radius of the planet. So that's how we play around with this equation. And in this experiment, if you open this simulation page, wait, okay, we have 24 students. So if you open this simulation page, we will simulate the acceleration on the planet. So if you click begin, so you see this is in a galaxy. This is the planet you will play with. So this is the planet. You click and you can adjust the radius and the mass. Wait, sorry. Did I recording? Did I record? Okay, I think yes.
Yeah, it looks like you are.
Okay. So so you can like decrease the radius. You see this ball, not this ball, this planet, and you can change the planet color. Let's make it more clear. Okay, so like a little pinky one, or okay, like a greenish color, and you can so you can adjust the radius by press the downward arrow or increase. So the first experiment, we want to start from the minimum values for the radius and the mass. So we go to the the smallest radius, and the mass go down to, you keep click it, And then you can, so if you click the planet name, it will change to different names. So what I want you to do here is you can follow the lab menu. So you basically click begin to start the lab, and click a ball on the top screen, change the ball characteristic of your choice. We haven't do the ball, but planet, okay, you can choose the, you can decrease the mass and radius and choose the name and color, record all the informations in table 1. So basically in this lab, we have 3 tables you have to fill out. So we'll go by one, we'll go through each table one by one. So the first you can fill out, after we change the information of the planet, you can fill out the mass, radius, and the name and the density. You see here the radius and the mass and the density. You just record all these 3 values to the table, and you can also I think you can just randomly name your favorite planet, like Cobalt, Kronos, and then you fill out here. So basically, you can fill out the values in the table of a planet. And then let's say we miss the ball on top screen. Okay, so if we look at the ball, so this is the ball. Okay, so you see the radius and the mass. And so the ball material is plastic, or you can click to be aluminum and zinc. So you just play with the ball and the planet. So you can change basically the radius, materials, the mass. I don't think you can change the mass because the radius can define the volume, because we know 4/3 pi r cubic. This is the volume, and the volume, if you time with the density of the material, then you can get the mass. So you cannot, you can only change the radius, which you can change the volume, and you also can change the density. Okay. Any more questions so far? And then same as the planet, you can change the radius and the mass. You can only change 2 things, but the density will be fixed. Let's say if we wanna increase the mass a little bit, then the density will change automatically because there's a equation, mass equal to density times the volume. Okay, go to this. And then, so then we play with a ball. We want to make a ball drop from a certain height. So here is, click the ruler. So basically what we do is we want to, so now we're on the planet. We say, okay, this is the planet and we want to zoom in. So then we're going to we're on this planet. And here's a ball, and we want to see, we want to observe the acceleration. So we put a ruler here, and wait, they have requirements for the ball. Okay. If you're choosing different ball material, like what we did here, then you will have your unique data. So we say now we have a zinc ball. We have a zinc ball, then we click drop. You see the ball drop. And then so from the menu, we wanted the ball drop at 4.5 meters head. Reset. So if you test, you can do one experiment and for testing, and then you click reset. Reset, the ball will be on about 2 meters. Then you click the ruler, the upper area of the ruler, then the ball will go up. So you cannot really control which position the ball is. So you just roughly make the ball close to the 4 meters. Then you click drop. So you get this graph. So when the ball is moving or when the ball is dropping, then they will automatically plot the graph. If you click the graph, you just left click the graph, and then you can see. So here's the speed and the time, and we know, like we also notice, like when I click the ball, it doesn't move for about 0.5 second, 0.6, 0.7 second, and then it start dropping. And then, so what I want you get here is to record the time. So the first time you see the table here, you have to record the velocity and time. So for the velocity, because at the beginning the ball is still, so its velocity is 0. So here you see the velocity v1 is 0, and here is v2. So this is the final velocity. So you can roughly read it's about 4.5 meters per second. Remember this unit. So you put it here, V1 is 0, V2 is 4.5 meter per second. And then you take the average. You basically add these two together and divide it by 2. And so this is for the first experiment for the velocity part. And we also have to fill out the time, so which you can read here. So V1 is from here, not from here because the ball is not moving. So we see the ball starts dropping. This is the V1, this is T1 and V1, yes. And then after the ball dropped to the ground, this is the V2. So it's about 2 point. So the first T1 is 0.7 second, and T2 is 2.5. So this is a T1, this is T2, and T average is used T2 minus T1. So any questions so far? So basically,
Yeah, I got a little confused about the V1, V2, and T1 and T2 actually.
Okay, so V1. So we're observing. So we are observing reset. So we are observing the process of the ball dropping. So if we drop, so cares about is the ball dropping process. So from the time ball is dropping, we record the time and the velocity. So and then the final speed and the time. So you wanna record the time when the ball goes through this distance. So you see drop. Then you have this graph. So because at the beginning, so the original, so from time 0 to 0.7 second, the ball is not dropping, so we don't count. Let's say the ball is staying there for 200 years, it never drops, so we do not observe, there's no acceleration speed in there, so we don't care. We only care about when the ball is dropping. Do I answer your question? So why we record from here and here, not here and here.
Yeah, so for this case, T1 would be about 0.7,
Right.
and T2 would be like 2.5.
Yes.
And what about V1 in this case? V1 would be also
yeah.
0,
So
right?
yes, because we are focused on these 2 points. You see these 2 points. It's hard. I don't know if I can make but we are focused on these 2 points. You can see that at this point, the x-axis and the y-axis. X-axis is 0.7 second. Y-axis is 0. And this point, you see x-axis is 2.5 a second. The y-axis is, is 4.5 meters per second. You just focus on those 2 points. So don't want to confuse you to check from where to where. You just pick 2 points. Actually, this because we are observing the acceleration, So any points along this line you can use any points, but to calculate the acceleration. But here they wanted you to record what is the initial position, initial time and initial speed, and the final time and the final speed. So you have to record these two. But if they don't ask you the initial and the final positions, then you can randomly pick any points from this line. So you can pick these two, because you see the slope. The slope is the acceleration speed. So the slope, they all have the same slope. So that means they have all the simulation speed. But just in this case, because they are asking you to record the first and the last position with the time and the speed, so you just pick these two.
Yeah, that makes more sense. Thank you very much.
Yeah, so you can fill out the first column. Is there any questions for how to fill out the first row? So the first row, the name, the mass, the radius. Okay. Who is asking question? Okay, no more. So basically, you have to practice.
I do have a question.
Yeah.
It's saying to reset it, and that we're gonna have to drop it twice. So I don't I know you're saying like the difference between the time, but when I'm reading through the actual lab thing, it looks like it says, click drop to begin the first run, then record data for V1 and T1, then click reset to make another run of the experiment with the same planet mass and radius, and then click drop again to get V2 and T2. So it's from two separate runs.
Wait. Let me see. So click drop to get the data for velocity, V2, and time. Click reset for. I already said. Click drop to get data for recording. Oh, they want you to do two.
Yeah, that's what I was saying. Yeah. It looks like you used to do it twice.
Okay, so basically what they want you to do is to, so here V1 and V2, you don't record from here. Let me see V1. Click on the grid button screen, record the default V1. And okay, so basically you don't have to record the first initial point. You just record the last one. The last one, you can read the speed and the time. Time, please remind, please pay attention. So the final time, you have to do the math before you fill out the table. So here is 2.5. Doesn't mean you have to put 2.5 in the table. You have to use 2.5 minus 0.7. That's the T1. So you basically practice twice. So then you put the V1 T1 in the table, and then you start the second trial without changing anything. You click reset and drop and put the values of V2 and T2 here. V2 are easy to get from, you just read it from the grade. But for T1 and T2, you have to do the math before you put the values into the table. And then you take the average and the average of the speed and the time.
I have a question regarding, I just did two different attempts, and while the amount of time from once it actually starts falling to the point at which it gets to the bottom is relatively the same, the amount of time before it actually starts dropping changed more noticeably. So we don't want to include the amount of time it takes before it starts dropping, because that does seem to also change in terms of our total time.
Right, because they want to, let me see, someone's asking. Changed every time you reset. Yeah, that's correct. That's why they want you get from, because if they're all same, then your T1, T1, T2 will be the same. Because
Right.
yeah.
So what I'm saying is, doesn't that mean then that we would say that the time would then be for this particular one that you've got up 2.5 seconds, because it's calculating from the actual time of initial drop to the point when it actually hits the ground?
Yes. So yeah, this here you can record the first one. Let's say if this is your first trial, then it's the T1 is 2.5 minus 0.7, right? Is that
Why
what
the
you mean?
minus 0.7? That's the part that I'm not confused about, because it actually starts its initial like being let go of at 0, and the 0.7 is just before it starts
Yes.
leaving.
Yes, so that's why. So if you include if you include this 0.7 seconds, that means your ball start dropping from 0, right? But your ball is not dropping, so you cannot take this one. You see, there is no speed. There's no speed, and the ball is not dropping. So you cannot take this part of time to calculate your acceleration speed, because it's not a. There's no sorry, maybe I click. There's no acceleration work on the ball. So there's nothing. There's no force work on the ball. So you only record the time after the ball is dropping. You see, when the ball start having speed, that's from here. Then you can start to record the time and the speed. So before let's say we can put it here, like we can let the ball stay here for 200 years. There's nothing. Like, do you mean like the over 200 years the acceleration speed is changing? If we include it like here, there's, let's say there are 200 years here. So if we want to include, if we want to calculate the acceleration speed, you cannot take the time here. I mean, the previous, before the ball is dropping, right? Does it make sense?
Yes, it does make sense.
Okay, so you only focus on this part when the ball start having a speed, and so maybe previously what I said it confused you. I want you to record the T1, T2, but I just want to make a one more time correction. So every time you record the you focus on the last the final position. So here the speed is easy to read, and then the final time. Final time is not here. Just remember that's not the final time. You have to minus the previous minus the time that was the ball was not moving. So this part is the final is T1, and this part is V1. So you see there's a triangle. Just make the triangle the x what do you say, the x distance. This part of distance is the time. The y, this is the speed.
So basically, we're only concerned about the time, the moment the ball starts moving until it goes to rest.
Right. Yeah. So you will practice. So each planet you will have 2 trials, and you have to have 6 work on 6 different to record the mass, radius, density, velocity, time, and then you make a plot of V average versus versus T average. So anyone knows what's the slope for this graph? So what about T over? Vincent, what did you say?
The acceleration.
Yes, correct. So the slope will be the acceleration.
I have a quick question. So what are these 3 rows for in the table?
This one, they didn't give you the 3 rows, like this 3.
Yeah.
They didn't provide 6 in 6. There should be 6 rows.
Oh, okay.
They only
So
give 3. Yeah.
So every time we change the mass and the ball weight, right?
Yes. Let me see how
Do
you
they
change.
give
Go ahead.
now saying, do they give like a specific mass and radius for all of the 6 trials or just one?
You change yourself. You see, you just change. Let me see if
It says on number 10 to just after each run to increase it by 1, the mass and the density. Just 1 click.
Yeah, one upward. Yes, mass and radius by 1 upwards arrow click. So each time you increase 1, each for mass and radius.
Yeah. So just to clear up, sorry. So we start at the very low, and then we increase by 1 for the each trial.
Yes, both mass and radius.
Got it. Thank you.
Okay, then you make a plot. So the plot will be in total like so you're supposed to make a 6 plot, but you can just make pick 2 of them to make a plot, 2 plots. Because I'm not very sure if you get the same velocity. So if you're on different planet, you see the equation here. If you are in different planet, you have different m and different r. So that the g is a constant. So these 2 will determine what kind of little g you have. So I'm not sure if when you change the mass and radius, you will get the same g. But I don't want you like maybe try to save some of your work. So you just plot 2 graph. Wait, just plot 1. Just pick 1 of them. Like all these 6 planets, you just pick 1 and plot a graph of V average versus T average, and then tell me what the slope is. Okay.
Professor, I do have one more question. And just why are we, if we're not changing any of the parameters, why are we running it twice? It's going to give us, wouldn't it give us the same exact speed? And as long as if we're subtracting the time that it waits until it drops from the total time, isn't it going to be the same every time?
Not really. I think so. Let's say this one. You see the red line here. It could be okay. You look at my arrow. It could be like go here, and then start.
Yes,
walking. And
I understand that, but you've been saying to subtract that time that before it drops, that flat line time, subtract that from the total, and that's gonna give us the same amount every time, wouldn't it? Because I know
I got the same as well.
Yeah.
Okay, let's do one more time. Try. This is 2.5 minus 0.7, right? And we want to reset, and we want to drop. So what do we see here? So so this is about 3.5, right? 3.5 minus 1.7. Yes. You will get the same. I think this is the same. 3.5 minus 1.7.
Yeah, it's the same.
Yeah, that's the same amount of time, and the speed is also. Yeah, I don't see there's.
Yeah, that's what I'm saying. So why are we taking an average of anything? It's always going to be the same.
Yeah. Yeah. Well, it's okay.
Easier for us.
Just like practice one more time. It should be the same. Because if you know the final speed and the time, and you can calculate. Final time t. Yeah, you can calculate this, and you know the distance is 4.5 meters, and you can calculate the acceleration speed by the final speed and the distance. You guys know which equation I'm talking about? If you only have a final speed, okay, you have the final speed and the initial speed, and you know the distance. So the distance will be the area of this one, and it's 4.5 meters. So you know which equation to use to calculate the acceleration speed. Let's see. square minus v0 square, oops, square equal to 2as. I think I'm doing my errors into consideration. Yes, so the equation I just put in the chat. So you have vt squared minus v0 squared equal to 2as. So then you can, because the s you know is 4.5, vt you know is, let's see here, is 4.5 meters per second, and v0 is 0. So you can calculate the acceleration speed. Well, it goes a little bit far. But yeah, that's the main point of this, the first part of the experiment. Any questions? So basically, just wanna address one more time. You measure six different planets, but you just plot one graph. You just pick one of the six, the average and the t average, and plot one. You don't have to plot six because it'll be very similar. I mean, the slope. You tell me what's the slope, and that's it. That's for the first part. And the second part, we have one more question. Plot a graph of planet mass versus planet radius. Determine the slope of the graph. So what's the slope of the graph? Mass over r squared. Anybody know? Anyone knows? Okay, look at this equation. Give you a hint. So if you plot m over r squared, what's the slope? Like they ask you m over r squared.
Force of gravity.
Yeah, it's a g over g, right? It's not a velocity, but it's g over g, because if you like on these two sides, you divided by g at the same time. So this will be 0. Sorry, this will be 1. This will be g over g, little g over capital G. So that's the slope, right? That's the slope of m over r squared. Does it make sense? You basically take this g to this side. You'll be on the numerator, right? Wait. Just g over capital G. And then they ask you determine the slope of this graph. Then it's little g over big G. And what is the significance of slope? So you know the slope times g. So what's that? What does this mean? So here the slope is g over capital G. And you time a capital G, what's the significance of this one? Okay, let me see. It's a force. Okay, let me draw, you just play with the equation. Let me find the whiteboard. Share. A G is a constant. The capital G is constant. So I think there's a number for that. It's like a very big number. So we know this G equal to G square, right? Now they ask you if you plot these two, then what's the slope? Then you have to find, if they ask you the slope, you have to find m over r squared equal to what? So this equal to G over capital G, right?
Yeah.
Because from this equation, you can derive it. You can derive from this equation. And then this is the slope. Slope of m over r squared. Oh, this is so hard, super hard. And then they ask you what the significance of the G over G times G. Oh no, they didn't ask you that. They asked you what's the slope of, what's the significance of the slope times G. So the slope times G. So we say slope times G. What's significance of this? The slope is G over G. And then this is slope and the times G. So you can cancel a lot. And equal to G. Oh my God. Right? So that's what you guys understand what I mean here? So let me see the chat if there are any questions. Here. Yeah, we divide both sides by G. So you see here, we just divided, if we ask you the slope of this one, then you have to understand what m over r squared equal to. So this one, you can, like, if you divided the same value from both sides, the equation wouldn't change, right? So this one, you divided by G. It's 1, so G is 1. And then you have to divide the G here. So it's G over capital G. That's the slope. So the slope is here, and they ask you what's the slope times G. So the slope is G over G, and the slope times G is little g. Any questions? Let me see the chat. No questions?
So for this question, we are not inputting any values. We're just saying the concept, right?
Yeah, you just explain. Like, I hope you could understand. You could explain like what I said here, and then you explain in your own words. Stop sharing. Okay. And then what happens to acceleration? Okay, the next question. What happens to acceleration due to gravity on planet as it becomes larger? So, so what will happen? When a planet becomes larger, the gravity becomes larger enough planet. The gravity becomes larger.
It should accelerate faster towards the ground.
Yes, the acceleration, yeah, the ball will drop faster. That means acceleration speed is bigger, right? When it drops faster, that means the acceleration speed is faster. Any questions or anything you think that you want me to clarify more? This is for the first part.
Yes, I get the what the slope equals little g or big G, but when it says what is the significance of slope times G, could you go over that again? You see, there's like a in between.
I think she's lagging a bit.
I think I froze her.
And she got kicked out. Professor, your microphone is muted.
I can, sorry. I don't know now. I cannot connect to the internet, and there are some issues. I could only use my phone. This is so weird. Wait, everybody's here. Oh my
Yeah,
God.
we're still here.
I really apologize for. So it just all of a sudden I lost my internet, and I tried to use the I use connect to my hotspot, but it doesn't, still it fails to connect. I don't know why. Okay, so I cannot share my screen now. So okay, so who is asking question before? I really apologize. Okay, but I think I still can check the who is asking question earlier.
Yeah, that was me. I was just curious about what was it, number 13, I think? Yeah, 13.
Okay.
Because we had just gone over the slope of the graph was little g over big G. And then the next question though says, what is the significance of slope times G? Because then the third question said, what happens to acceleration due to gravity? It becomes bigger. We did that, but I think we skipped that middle one.
Okay, so you don't understand what's the so here first question you understand how to define the slope of the graph?
Yeah, I mean, I just want to, I mean, it would just, I'm assuming if the slope is little g over big G and we're multiplying it by G, it's just little g, right?
Yes.
Okay.
They're just putting a math problem.
Yeah.
Yeah. And then you have a question for the acceleration change after when the gravity becomes.
No, that was it.
Okay. Yeah, sounds good. So can we do go over like lab so the part 2 and the part 3 very quick? Oh, there's no part 3, only part 2. Let me try. I don't think I can connect now. So, or you guys want to work on the part 1 and then when we got we meet another time, or we finish this quickly? Okay, I'll just go over a little bit about part 2. If you have any questions, please email me. And another issue is like, because my computer is running very slow, I need to go to get it fixed. It takes about 14 days.
Professor, you could also record like you explaining part 2 when you have time and put it in the YouTube video with the recording, so we can go back and check if we need help.
Okay, yeah, that's what I would do. Yeah, I think I'm recording now. So okay, so I can still use my computer, but I can tell you what I do next, and then you can we can do it at the same time. So if there's no more question for part 1, then we go to part 2. Okay. So part 2 is asking you to explore the acceleration due to gravity on planet with the same radius but different mass. So in this case, you would not change the radius. Remember, we change the radius and mass by click one upwards arrow each time. But this time we don't change the radius, we only change the mass. So let's see what we do here. So then click the planet on the top of screen, decrease the mass radius to the minimum possible, name and record the information table 1 below. Okay, so you start with the minimum mass, and the radius you keep the minimum and don't change. If you look at the table now, so you see it's same table. You have a planet, velocity, and time, but this time they already give you the minimum radius, so you don't change the minimum radius. You only change the mass from the minimum mass. And if you go to the simulation page, I'm surprised I can still play with the simulation part. Okay, let's go to the minimum radius and minimum mass. Minimum mass is 6 times 10 to 23 kilograms. And you define your favorite planet color and planet name. And then what we do here is, if you look at the part 2, step 2, click zoom in, then click on ruler. So basically, it's like what we did before. If you go to simulation page, then there is a ruler on the top. You click ruler. Wait, you have to zoom in first. Zoom in means you go to the planet. So you zoom in and then you click the ruler. So the ruler will show up. And then, so still make the ball at 4.5 meters high. So you just click the top of the ruler and move the ball up. So you can really control the ball, which position precisely, but you just make sure the ball is close to 4 meters. We just assume it's 4 meters. Even now the ball, at least for my ball, it is like a 4.2 or something, but we just assume it's 4.5 meters. No, we make only one graph. So basically, I just want you know how to plot the graph, and you just make one. Don't need to make 6. For the question in the chat, and then if you look at the menu, click drop to begin first round of the experiment, and click the grid on the bottom of the right screen. Record data for velocity v1 and t1. And click reset, make another run planet, and drop again and record v2 and t2. So basically, you see from step 1 to step 6, you're basically doing the same thing, but this time you don't change the radius. You just record the density, record the mass, the density, the velocity. Velocity you will measure 2 trials, and put the 2 velocity here and 2 times here. It's basically like the first step, first part of the experiment. I think it'll be best if you record. Oh yes, I think I could wait. Explain there. Yes, sorry. I think I know what you mean. Wait, can I flip my camera? Okay, so can you guys see?
Yes.
Okay, this will be good. I want to pin the screen because I cannot see. It's too small. So what I do here, okay, I start over. So click the planet. What we do here is zoom out. So the planet, you see here. Wait, this will be better, right? So you click the downward the arrows to be the minimum radius and mass. And then, so for the part 2, you only need to increase mass, but change the radius the same, keep the radius the same. So the first one is the minimum. You see the graph, the table here, you have the mass. So you put 6 times 10 to power 23 kilometer as a mass. The radius they already given you, because you see here, the radius is always 4 times 10 to 6 meters. And the velocity here, you see the velocity, and they record this to data to this table. And then like after you so the first one, we get the minimum mass and the density, we go zoom in. So that means we will go to this planet. So you say zoom in, then you click zoom in and go to planet. And then when you go to the planet, you need a ruler to measure the heads of the ball. So here, so it's 4.5 meters. Then we say, so 1, 2, 3, 4. So 4.5. I know it's not very close on the 4.5, but you just take it as 4.5. Then you click drop, let the ball drop. You see the ball dropping. And then you click this graph. You just like left click, and then you see here it's the same graph as the graph from part 1. You take this point, you take the V1, which is the y-axis. So this is the y-axis. So this height, and the x-axis, which is this part. Just make sure when you measure the time, measure T1, you make a 3 minus 1.1. So this 1.1, we don't take it. Can you see clearly? This this 1.1 is not in the acceleration process. So we wouldn't include the 1.1 seconds. We only take the, you see this triangle. So every time you want to know what takes into consideration, you find the triangle. So the triangle under the acceleration process. So this is the x-axis, which is the T1, and the y-axis, which is V1. And then if you want to exit from this page, you just click one anywhere. Click anywhere, and then you go back to here, and you click, because the ball is on the ground now, and you want to reset again, and then the ball will go up. Then you drop again. You see, and then they plot a graph for you. So this is your second trial. The second trial is for your T1, T2, and V2. So at this time, you see, now the velocity is still about 5 meters per second, and the x, which is the time to T2, will be, okay. Let me read, 2.7 or 2.6. Let's say 2.6 minus 0.7. 2.6 is 1.9 second, right? So you just take this triangle. Can you see my arrow here? Take this triangle. This is the x. This is y. Y is the velocity. So if this is your second trial, this is V2. This is T2. Okay. So this basically, you fill out the first row of this table. You have you record the mass. The first one will be the minimum mass, and the name you can give your favorite name. It doesn't matter, and you record the mass. And then because when you change your mass, let's say this is 6, this is 7, this is 8, then your density will be increasing, because the radius guaranteeing the volume will be the same. So when you have a bigger mass, then the density will be bigger. So basically, you these two, for the planet, the mass and density you can get from the planet. Wait. Okay, so whenever you have to change anything from the planet, you have to zoom out. So you have to, like, how to say this, a God perspective. You see everything so small. And you see planet, then you can change the radius. We don't change this time. We change the mass. So each time we increase a little bit. So it's 7. 7, the density, you see, okay, let's say the mass is 6, it's 2, 2, 3, 8. When it changed to 7, to 6, so the density is increasing, right? So basically, you have to fill out 6 different planets. So also they give you only 3 rows, but please fill up yourself with 3 more rows, and you have the same radius, and increase the mass from 6, 7, 8, 9, 10, 11, and the density you just read from the page here. They will give you. They already calculated for you. And then the V1 will be the first trial. V2 for second trial will take that. Then you take an average, same as the time you record the T1 for the first trial, T2 for the second trial, and then you take an average. Okay. Yes. Any questions so far about how to do the experiment? Okay, then let's see the question. We want to study for the questions a little bit. By increasing the planet mass but maintaining a constant radius, you're in effect increase the planet density. Okay, what effect does the increased density have on average time for the ball to fall through 4.5 meters? So when the density increases, what effect they will put on the ball falling? Any thoughts? So
Probably fall faster.
yes, yeah, the ball falls faster. And question 10, plot the graph V average versus T, determine the slope of this graph. Let me see, when plotting the graph V versus, okay, let me see the question, okay. When plot the graph V versus T, I assume V will be, this is average, okay? Will be one on axis and T will be on another. So you see, wait, I need to say here. You see here, V average and T average. So you see here is the V average and T average. Let's see the first one is, actually you are supposed to measure V1, V2 the same, but sometimes there is some errors, and plus the grade is not very clear. You don't know when the different people move with different values. Maybe these two are slightly different, but you don't think, okay, I plot V1 T1 versus T1 or V2 versus T2. You plot V average versus T average. So this only one value. So and this value is close to both of this V1 and V2. This T average will also plot very close to T1 and T2. Okay. I got the idea of average. I will just confirm that it gets plotted on y-axis and t. Yes, that's right. Otherwise, you will have a. So basically, whenever they ask you A versus B, that means A will be the y-axis. B will be the x-axis. So this is V versus T. That means V will be y-axis. T will be x-axis. Okay, sorry, maybe I misunderstood your question. Okay, then wait.
Quick question.
Yeah.
Do we make 6 plots or one plot like the previous?
One plot is okay. I don't really care. Yeah, I just make one plot. Okay.
Just to clarify that, you want just one graph with one plot for the total average time and total average velocity, like out of all.
Yes, you just right. Yeah, you pick one of the 6. You just get one graph. That'll be fine. What does the slope graph tell you? Okay, what's the slope again? They ask you again. So I'm sure you already know.
Over big T? It wouldn't be little g over capital G?
Okay, you have to remember here he's saying V over T.
It's just acceleration. Wouldn't it just be acceleration?
Yes, that's right.
Oh yeah.
So yeah, this is the only acceleration. They play a tricks earlier, like here they play a tricks. They just this one from part 1, question 13. They play a math problem, a puzzle to confuse you. You see, but here what they ask you is V over T. So this is just the little g. Okay. And between gravity and increased density. Okay, slope. Okay, they ask you, yes, we know the slope of this graph is little g. So what happened to the little g, to the slope, when the gravity is increasing? Like, what will happen to the little g when the increase the density or the increase the mass without changing the radius?
It gets bigger.
Yes, it gets bigger. Do you know why? So anytime you want to know why, you have to find the math, the equation. Where the equation? Here. Here, this is so important. So when you increase the mass and you remain the radius, can you say clearly? So when you increase the mass, you keep the radius constant. So this will increase. This is the capital G is constant. So that means the G will be increasing, right? So math is our best friend. Whenever we have any question in physics or in chemistry, math always be the solution. So whenever you have a concern, you always find a right math equation to explain why everything is changing, or what's the relationship between A and B and C and D, okay? So that's why math is very interesting, fascinating. Okay, I got K. Okay, then when we see, for question 10, so the slope of the graph will be increasing as the gravity and the density increase, right? And okay, sorry, my arms is a little bit sore. So question 11, what's the name of such body, a planet star, which is so dense that it's difficult to impossible to escape its gravitational force of attraction? Anybody knows the answer?
Black hole.
So yes, black hole. Black hole, even you don't see any light from the black hole, because even light, they cannot escape from its gravitational force. So that's really amazing. And the question 12. Okay, question 12 is a little bit tricky. You have to be very careful. So they want you already got your data points, but they want you to check the accuracy of your data points in the graph. So in table 2. So they give you another equation, dy equal to vt. Wait. I don't see my mouse here. Okay, so dy equal to vt, vit average plus half g t average square. So dy here is the vertical distance fallen, which is 4.5 meters. So this is d. V is initial velocity. So see, they say vi initial velocity. So what is the value? Anybody knows what's the value of initial velocity? So when the ball starts dropping, what's the velocity rate of the ball?
It was 0.
Yes, the value, the initial velocity is 0. So if d equal to 0 times t plus 1/2 half gt squared, then this part will be 0, right? T times 0 times anything equal to 0. So you can simplify this equation to be where d equal to half gt squared. And then how you get g? You basically play a mathematic game again. So g equal to, you see, if you times 2 on both sides, this is 2d equal to gt squared, and you divided the t squared on both sides, then 2d over t average square equal to j, which is the equation they give you here. So the j average equal to 2d over t average, right? You know how it transformed from this one to this one, or even further, how this g transformed from d, this equation, let's call equation 1, and then equation 2, and then you get the equation 3. Sorry, I didn't see there's so many chat. Okay. So it's easy to understand, right? The first is because V0, Vi is 0. So you D equal to half GT squared. And then you just take G this side and the D over this side. You get a what? G equal to D over T average. And the dy, what is dy? dy is when the ball falling from 4.5 meters. So that means dy equal to 4.5 meters, right? And the T average you can measure. You can just take the value T average here to here. T average, sorry, that's not. Okay, you get the T average. Then what they want you calculate is you have a mass G. They want you use this equation. Sorry, can you say? They want to use this equation to calculate the G planet. You fill the values here, and then from table 2, V average over T average, you fill here, and then you can see if they're same. I can tell you they're very close because you just use 2 different methods to calculate the G. And then, yeah, here you should be fill out for 6 rows, 6 planets. Okay? Any questions for question 12? That will be the last question.
I have a question on the table. So okay. So for example, in column 1, right? I mean the row 1.
Row 1, yeah.
So I picked a planet name like that I have previously done. So I put the mass of that planet, and using the equation on above, I find the little g.
Yeah.
And I get the last column from the previous table and
yes.
compare if they're the same.
Yes.
And this whole time the dy is equal to 4.5 meter, right?
Yeah. Do you know why? Do you know why it's 4.5?
Because in all the experiments we dropped it from 4.5 meters above the ground,
that's
right?
Correct. Yes, correct. That's on point. So basically, you the equation to calculate the values for this column, and this column, and even for when you calculate the G, you still have to use the value from table 2, which is T average, and you calculate this one to put here, and you use V average over T average, both from the table 2. So V average, my God, V average over T average, this is also the G, little g, right? So these two supposed to be the same. The reason why they want you calculate this one is to check the accuracy of this, the little g from table 2. I see someone is asking question. I have to leave. Okay. Okay, Mark. Okay, so any questions? Let me see what time is now. Any questions? Is that easy to understand? Otherwise, I'll take attendance now. Any questions so far? No?
No.
Okay, wait a second. Let me check. So, okay, let me see. Oh my God. I still cannot connect to the internet. So then we will meet next in 2 weeks. If you have any questions, you can schedule individual meeting with me. And I will not have my computer for 14 days, but I will. We can use iPad or any other media. Okay.
Professor, would you be able to go through problems before the physics test we have?
Yeah, if you have questions, yeah, feel free to ask me. That's what I'm here for. When you have the midterm?
The day after next week. Next Wednesday.
Wait. Let me check. But I will not have my computer though. But let me see calendar. Oh, I cannot go here. So today's 9th. So next time is 17th. Your midterm is 17th.
Yes, I believe so.
Yeah. If you have questions, you can ask me. We can schedule a time. I think iPad. I can use the iPad to explain something to you. Yeah. If I really want you all can. It's a midterm. So yeah, please send me your questions before Sunday. I think or Sunday. Then I could have time to go over, and then we can like discuss a little bit on Tuesday, if that works for you. Because if you give me, then probably I'll take time to think about it. Then let's see, any chat. Yeah, we can definitely have a recitation. Yes, it's all up to you guys. But yeah, next week I'll use iPad to do the recitation, and I could write. So yeah, basically we don't need to share screen. We can just work on the same problem, and or you tell me what you are confused about. Then we can definitely start from there. Same time, because other students maybe have a different schedule, and we want to start we want to use the same time. So it's 2 p.m. 16th. Okay. So we're gonna meet. Yes, the lab will be due Tuesday 16th. Lab is very easy. You can spend like maybe 1 hour or 30 minutes to finish the lab, right? But yeah, if you have any question for the lab or for your recitation, just email me. Yeah, if I didn't reply, but I will. Yeah. So after I will check your email and answer your question later. Let me see, take attendance. Wait, attendance, that's not. So we will meet next Tuesday. It's not mandatory. Mandatory. You don't have to come if you don't have questions. Let me see, teaching. City College. Okay, this one, 2021. Okay, so this is lab 3. Lab 3, okay. Anika is here. Can you say, wait.
Here.
Okay. And Ali?
Here.
Anika Tessin. Tessin is here. Tessin is not here. Yasin?
Here.
Alexander.
Here.
Fadia.
Here.
What? Arthur. Arthur Fong. Michael. Michael is here.
Yeah, I'm
okay.
here.
Peter.
I'm here.
Mark, I think he left early. Yang. Ziyang.
Here.
Hassan Munino.
Here.
Jack. Jack is here. Jack. Ellie Hongnig. Okay, this Ellie. Okay. Joshua.
Here.
Josh Path Kumar.
Yeah, that's me.
Andy Matthew. No. Mohammed.
Here.
Mia Nafil.
I'm here.
Sabia.
Here, Professor.
Marmont. Thank you. Marmont. Musa.
Yeah, I'm here.
Anis.
Here.
Anis. Shavar.
Here.
Camel. I think Camel maybe dropped from this class. Bujar. Bujar. Vinsar.
Here.
Amr. Amr. Okay, here. Amr, then Heather. Heather. Okay, Evan.
Here.
Michaela. Michaela, right? Sorry, I'm sorry. Okay. Okay, then if you have questions, please attend next Tuesday's meeting. Then that will be all.
Excuse me. I stepped away for a second. I had to do something. Can you mark me here? I'm Mohammed Mazur.
Sorry.
You just took attendance, right?
Yeah.
Yeah,
Who
I
are-
stepped away for a second.
Hello?
I don't know if you marked me here.
Oh, what's your name?
Mohammed Mazur.
This one.
No, it's like 2, 3 up. It's Mohammed Mazur.
Muhammad.
Yeah.
Muhammad. This one, Mazar.
Yeah.
You are here, right?
Okay. I just had to make sure because I had to help my mom with something.
Okay.
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 Hello.
Hi.
I think you marked me absent.
What's your name?
Hater.
Hater. No, I think you're here.
Okay.
Hater. No, you're here.
Okay.
Oh, I think you must be absent too.
What's your name? Why you are not?
My bad. Kemo. Sorry, I wasn't speaking.
Okay.
My
Oh,
last name is Robinson.
And one more question. You didn't submit any of your report.
I can submit it today. I was having internet connection issues.
Okay, just yeah. Okay.
Oh, I was here the other times too. You could check the Zoom link.
But I needed you be here to listen to the lecture, not just log in and do your own stuff, right?
True.
Yeah. Sorry about that, but you can next time. You can whenever I call your name, you can be here. Yeah, but I cannot change previous things because I cannot verify if you are here or not.
Oh.
Yeah, sorry about that.
See the who joined the thing like on Blackboard Collaborate. I thought you could see who was a participant during the video chat like on Blackboard Collaborate Ultra.
Oh, I don't do that. I only take attendance when I call your name and you are here. And because like I know a lot of students, they don't they just open the Zoom and they don't sit in the lecture. So yeah, if you are in a lecture, then you will hear my I'm calling your name. But yeah.
Wait, sorry. I was in the bathroom. Was they marked as absent?
Yes.
Sorry. I was in the bathroom because I was like doing the you know what. Yeah. So sorry about that. I was kind of in the bathroom.
Okay, where's Arthur? Here.
Yeah. So sorry about that. I was kind of.
Okay. It's okay. Yeah, Arthur, like I would double check the on Blackboard. I see if your lab report included part 4 for the first time. Then I'll get back to you.
Yeah.
But now my internet is not working. Maybe I'll get back to you later.
Definitely, that's fine.
Okay. Yeah, that'll be all for today. Thank you, guys. Thank you so much. I really apologize for the internet issue. Okay, bye.